hand. And also I will ask you to yell in some kind of functional programming words what you have heard about. So that's helpful if you unmute yourself. All right, is it starting? All right. So first things first, I will be using my iPad to show off some stuff. You will see handwritten and text written stuff, which is because I was lazy sometimes to handwrite everything. I'm sorry about that. It's kind of a mess, but it will be fine, I promise. And today we will be talking about, well, what is functional programming in the beginnings and why we would use functional programming. Actually, I can give a quick answer to that. Functional programming tends to give you a lot of structure, which is mathematically proven. And that means that you don't really have to be sure of your implementations, because if they are proven, then they will work if you know the right tools. And it's like Lego, you stick things together and you make bigger things from like just like you do with Lego. So all right, let's start with changing. We have a camera on. It's fine. So let's start with changing to my iPad. So we have several. Maybe this will get some. So you should get used to this, but I know it's weird, but it works. So we have several object-oriented patterns, which are these. I don't know what half of these are, so don't feel weird if you don't too. But I can give the equivalent in functional programming to every single one of these, I guess, because if you see, for example, single responsibility principle is basically functions, and open-close principle is also functions, and dependency inversion principle is also functions, and then you see basically you give functions to everything. This means that, or the takeaway is that basically functional programming patterns are somewhat different than OOP. And the first thing I want to do is to, so if you have, if you feel the enthusiasm, you could yell in some kind of functional programming words. And I wanted to help you by just providing some guideline. You have to think about functions and types. If you don't want to do it, that's all right also. I will write here some words about which we want to talk. So anyone?
Map.
That's a function.
Fold.
Abstraction.
You can try
polymorphism is another one.
Things, some general things as well. Sorry, again? Come again? I didn't.
Polymorphism, I guess.
Polymorphism, right.
Monad.
Oh yeah. Maybe you have heard that monads are just
encapsulation.
Pandofunctors. Yeah. We can talk about that as well. Monads. Okay. Monad is actually a type. So again, please. No one else?
Encapsulation.
Encapsulation. I think that's more of an OOP thing, but yeah, we can write it here. I'm sorry, I'm writing really ugly. Sorry.
Yeah. Recursiveness or recursive.
Currying.
This is an important one because we cannot do loops basically in pure functional languages, and we will talk about pure functional language today, which is Purescript. Maybe you have seen some of my articles about that. Okay, so the other one was, sorry, I missed that again.
Currying.
Curry, yeah. This is also an important one. It's not the food. It's when you just partial apply function parameters one by one. So we will talk about this as well. In functional languages, this tend to be automatic. All right, we are missing out on types. So anyone on some kind of types? No one. We have a type system in Purescript and Haskell, which is called Hindley-Milner. We will be talking about this one, and also types in functional programming aren't classes. So meaning they have no behavior. These things are also important, and they can be composed.
And they're also immutable.
Yep, that's also important. Immutability is important because functional programming tends to use this all the time, and when you have immutable data structures, you can use parallel programming out of the box. You don't have to symlock and I don't know what, because immutability just gives parallelism out of the box. That's a really cool thing. About functions, I want to talk about pure functions and also total functions. And did I miss something? Okay, so functions are first class. And functions are also just data. So they are things we can pass them around. Not a date, sorry, a data. So we can pass them around. And okay, I think this is enough. So can somebody tell me what a pure function is?
No side effects.
For same input returns the same output.
Yeah, so pure function is basically just that. It does no side effects, which mean it won't launch a nuclear stuff or do an HTTP request or something. In functional programming, you have to note in your type signature that you are doing a side effect. It's not that we don't want to do a side effect, we want to do it in a controlled manner. So pure functions are cool. And can anybody tell me what total functions are? If not, then total functions are the functions that are so for every input there is an output. Let me give you an example of this. So for example, in Java, when you write a division and the division throws an exception when you divide with 0, that's not a total function because you are not considering every input. So, for example, yeah, that's an example. Fold is just reduce in functional languages, but we will talk about that later. And abstraction is actually a really important thing in functional programming. That's what monad and functor and applicative types are. We will talk about this as well, especially functor and how map does its thing and how we are associating iteration with func or map, but it's not quite that. So yeah, I will switch to composition right now. First we will talk about what is a type. So types are basically sets of values, and let me just turn in the reminder of that these are types. So between types we have functions which are mapping from valid inputs to valid outputs, and so types have no behavior. That's really important. We have something else for that, which is called type classes. Type classes are like Java interfaces. They define some kind of behavior of some general structure. Okay, so for example, int is a type, customer is a type, and in functional programming we are try to be as generic as possible. So we try to strive for polymorphism and also pure functions and total functions. Actually, if I rush too much, please call me out because I tend to do that sometimes. So if we have an understanding of what is a type, then we can talk about composition. And let me just give you a small explanation of what this legend is. So the empty circle means that it's a type. And if I write or show a colored circle somewhere or a colored shape, that means that it's a value. So if I turn on a function from here, I just created something here. This a function, which is a function which called a, is a definition. You see that it's turning circles to squares, basically. And if I turn on the other part, so not this one, then this is a function call. I feed in a circle and it spits me back a square. This is all right. So we will have another function as well, which does similar. Function b is basically taking a square and spitting back a triangle. And if we call it, it seems like it's doing exactly the same thing. And if we compose these together, then we will get something like a function which takes a circle and spits back a triangle. So we stick them together like Lego pieces. And you could notice that we never have a square in the whole process, which is important. And I will show you some examples of these. So let me switch to my browser. I have actually written, I don't know, can you see these code? Is it all right? It's readable?
Yes, yes.
Okay.
You may need to increase a bit your font size.
Oh, I'm not
Or
sure.
you remove if you could remove the debugger or make it smaller, because when I think this page is a bit responsive, and just press Ctrl+ to increase the zoom.
I'm not sure if I have that, but can I zoom somewhere? Because I am on a Mac. What do you press on a Mac?
Command+ in your Mac.
It's not working. All right, let me just
and plus.
Fn and what?
Command and plus.
Command plus. I don't have plus. Oh, I have one. Okay, great.
There
Thanks.
you go. Thank you very much.
Great. Okay, so we have I have added here several types, and this is the thing I tried to draw the last time. I think we have a lot of TypeScript developers in this call, right? I hope so. But if you are a Java developer, it's pretty similar, so it's fine, I guess. So we have a point which is just an X and a Y coordinates, and we have a circle, which is a point and the radius center, and also a square, which are constructed from 4 points. I know this can be easier, but for the sake of it, it doesn't really matter. And also a triangle, which is 3 points. So we have a function b, sorry for the order. If we have a function b which takes a circle and returns a square, then we do something with this circle to construct a square from it. It doesn't matter what we do. The important thing is that this b function is taking a circle, returning a square, and this a function is taking a square and returning a triangle. So we want to compose these together, and this O is basically what I wanted to use, because you tell compose in category theory, you use this little circle to note composition, which is read by B after A. For some reason, I don't know why, but it's read like B after A, and it's just calling B with the circle and then calling A with the result. So we can generalize this to compose, which is having 3 types, and you just apply F after G. Yes, sorry, that's the correct pronunciation. So I don't really want to show this. I think you understand all of that. I can show, however, some kind of examples. I have a fizzbuzz and at my gists, and let me just zoom in. So I don't really want to show all this TypeScript example, but there is an ES6 compiled version. So this is just a range which takes an m and an n, and it creates an array from that. And this is compose, which is somewhat different compared to what you have seen. It takes an array of functions basically, and the first function, and it just calls them together, building a bigger function from the safe small ones. And there is a safe mode, which is basically just dividing, if only dividing if there is a number, right? So the first example here of currying is this one. In JavaScript, you can do currying like this. So currying is basically similar to partial application. You feed in your parameters one by one, and then you can create a generic function. So this is a generic function, and you can create special functions from this by calling them one by one. So fizz would be like if it divisible by 3, then put out fizz, and it will be waiting for the value as the last argument, as you can see. So we pass in divider, we pass in the replacer, and lastly we will pass in the value, but we don't do that yet. And all of these are the same, it's just different parameters, and then we compose them together. So we create a new function. FizzBuzz will be called first. It replaces everything which is divisible by 15 by FizzBuzz, and then the same happens with buzz and fizz. You can see that this actually works. If I just put it in here, it will create an array like this. I guess this is an unusual implementation. I haven't seen it before, but I was fiddling around with functional programming, and it is something like this. Safe division, just a fun fact that safe division is necessary, because here, if you just using divide, then you will get a string modulo 5, for example, which evaluates the false, because none equals anything is false. So it's just that, and that's a pretty awful thing to exploit.
Hey, Daniel.
Hey, sorry, yes?
Can you go back to line 47 and explain what the compose is doing? I know you went kind of fast through the.
I'm sorry.
You composed.
Sure.
So 43, 44, and 45, you created 3 closures, or 3, I guess, curried functions.
Yeah.
Right. Can you explain what's happening on 47?
47
and
is
why you need to put them together.
Okay, so let me just open a console for that. Can you? I guess you cannot see this pretty well, but it's something like it's pretty similar. If I just do something like, let me edit this.
You can still press Command plus to increase the zoom in debugger.
I'll do that. Oh, sorry. Command plus. Oh, great. So basically what this is doing is just letting us write the code in point-free style. If you have a map, you can pass here a function, and we, instead of just doing something like taking a value and calling it with buzz and FizzBuzz and buzzing in the value, instead of this, we can just create a new function which merges these together in this order. So FizzBuzz will call first, and buzz, and then fizz. And this is the same. So this is what compose does, basically. What we have seen with the TypeScript example is just doing it so you can pass in any amount of functions. Is that clear? Is this a good explanation? I'm not sure. Okay. Okay, so we have compose, and what we have to talk about next to continue this talk, I'm not finding my pen, sorry, is to see that not just functions can be composed, but also types. So there's a thing in functional programming called algebraic data types. And you have seen this in TypeScript as well. You have the sum type and the product type. When you, for example, these are just examples. So if you multiply together a set of people which are a type with a set of dates, you can get a birthday because it's both that data. And the sum type is somewhat different. It's a choice. So a set of falsy values and a set of truthy values would be, for example, set of falsy values is obviously just false in the context of Boolean, and the set of truthy values is true. So you have either true or false. So this is the sum type. And you can create some more complex stuff from this. If you just use sum types and product types together, basically you can do arithmetics on these kind of types, and the result will be some more complex types. So this is type composition. Anybody has questions about this?
Do you have an example of this in TypeScript?
Yeah, in TypeScript.
Or just in code?
I didn't create that one, but I can come up with something pretty fast, I think. So product type would be, well, for example, if you have a set of people that's, let's say we have a type people, which is a, I will pseudocode here, but I guess you will understand, it's an array of person. And dates are just dates. So type birthday would be something like people and dates, I guess. So this, but I will show examples in Purescript if that's fine. So let me just continue. Yeah, I will show a screen of Purescript first. So Purescript is a functional language, and the interesting thing about this is that, sorry, I will have to zoom out a little bit. Yeah, so the important thing about this is that this has some interesting annotations. For example, this is what I have said, that this is the Hindley-Milner type annotation. And this is an ID function in Purescript. I will show you more of these examples later. But let me just give a quick explanation of what you see here. So this symbol here, sorry, let me just pick a pen. So this symbol here, this one is meaning just for all. You have to denote that in Purescript that for every A, this is true. If you give me an A, I will return you another A. This is polymorphism in Purescript. So it's almost similar like saying any in TypeScript, but there are some subtle differences. And if you go down a line, that function, which is the second one here, sorry, here, let me just read this out to you. That it means that for all A and B, give me a function from A to B and give me an A, and I will give you back a B. These A's and B's are type variables, so it can be passed an int or a person or anything. You are just mapping from A to B, and if you give an A, it will return a B. If you see the implementation, it actually in Purescript, function calls and function definition is and separating parameters is done with white space, which is kind of weird, but this function is the function and name. Sorry, I always try to write in the wrong screen. So this is the function name. this is a first parameter, A to B, and this is some data which is the type A. And then the implementation starts here. You call another function with the data. And also you can do currying. It's built in. So for example, we see that here is plus 2 or times 3, which is just applying one number to the plus function. Actually, in Purescript, every operator is a function and every type is created or implemented in the manner, in the scope of the language. So you don't have like built-in types and operators. It can be created with the language. I will show also examples for this. So you have currying, and this can be done for any number of parameters. You can provide one less and you will get back a function which is waiting for the last one. That's always true. And this arrow is basically saying that this is a function and it's right associative. So if you would write it out, it would look like type and you can put parentheses here. And this makes it obvious that if you feed in a type, just one, you will get back a function which is waiting for one type and it will return another type. Not sure if this is understandable, but I hope so. So you also have built-in composition, which is also a function. This one feeds the output of this function to this one. When you call it, you feed something here, and it will be passed and then call the other function with the output. So you can create new functions in Purescript like this. And let me just I do have something else. Let me just show you some real code here. So I can I also zoom in here? Yeah, great. Do you see the screen correctly? Is it readable?
Just a bit bigger, that's
Yeah.
it.
Great.
Yeah.
Okay, so basically you have primitive values. I don't really want to talk about this as much. If you have a value, it will be inferred. You don't really have to do all these annotations like you see, for example, here that Bob Ross is a person and Leonardo da Vinci also a person and list of people is an array of person. You don't really have to do this. It will be inferred because Purescript has a really strong inference, but it's advised because you see what it is for what it is. Actually, VS Code has a really great support for Purescript. Maybe I should have started with what is this. All right, so let me just try that. Purescript is basically a language which is similar to Haskell, but it's not lazy. Lazy meaning that you cannot create infinite structures and streams because Purescript compiles to JavaScript, and basically that is why, because you have to deal with the event loop and stuff like those. In Haskell, you can actually create lazy structures and infinite lists, and you can take several items from a lazy list, and then it will be calculated only when it's necessary. In Purescript, this is not the case. You have strict evaluation, but other than that, it's really similar to Haskell. It just compiles to JavaScript, and you can also have React bindings, for example, and you can write React in it, but you can also have backend code in Purescript. Actually, I have created a repository where you can check this out. So I mentioned that we have primitive types, like this m is an int, and you can create a sum type like this. So if you use the data keyword, I will create a Boolean, and this here, this lie and fact, is actually a new word in the language from now on. So this is how the original Boolean is defined in the language as well. It's just included in the prelude module. And in Purescript and also Haskell, we have some kind of things which called type classes. So type classes are, as I have told before, pretty similar to Java interfaces. For example, here's a show type class, and everything which is showable, for example, my Boolean is showable if I define an instance for the show type class. It can be printed, so you cannot print values by default because Purescript doesn't know how. You have to implement the show type class, and the show function is just looking like this. For all A, you have an A which is showable. This is a type class constriction, and if you give me an A, I will give back a string. That's what it means. So you can also derive instances if it's really simple. For example, EQ is also a type class. It can, if you derive EQ, you can compare these values. So lie will be equal to lie, and fact will be not equal to lie as well. And another type class is ord, which is orderable. So if you derive it, then the first one will be the less smaller than the second one, so you can compare these. And all right, so here's an example of a product type. You can just show stick these together, and my product type will be consisting of a Boolean, a number, and a string. And I actually can show this because here's a REPL, the readable print loop, and I can create an instance of this. So that's done by using the type constructor. This is my product type. And if I have a value of x, which will be my product type, and I give it I think a lie. Sorry, you don't have to double quote those because they are existing in the language from now on, and number and a string. Then I will have to set these an int, I'm sorry. And if I just want to write this out, because we are a member of the show type class, we can write this out. So this is a value here. If you actually press here the $T and the X, you will see that it has a type of my product type. So we can define other kind of product types. Record is actually a product type, which consists of these values. It's just a JavaScript object. This is how Purescript represents JavaScript objects. And you can also print a person. So if I would say Bob Ross, it will print Robert Bob Ross. And also you can print Leonardo da Vinci as well. The more interesting thing is that you can print arrays as well by default, because show is defined for arrays. So list of people would look like this. And we see in this ID, and this is a lambda. So you pass a function to a variable. This is the same, these two. And basically this is all in this section. So the next thing I want to talk about, we know a lot of things right now, so we know about type classes. So I want to talk about what map is in our heads. So in JavaScript, we tend to think about map as some kind of iteration. And can somebody tell me anything other than map? What is map? Or should I just go on? I'm not sure. All right, I will go on. So we have this notion of boxes in functional programming, and map, let me give you a definition of map, and let me just read it out to you. It may be easier if I just hover in here. So do you see this definition here? Is it readable?
Yep.
All right, great. So map is a function which for all a, b, and f, there is a type class constriction that f must be a functor. And if you give me a function from a to b, I will give you back a functor of a. And give me a functor of a, I will give you back a functor of b. So this is really cryptic right now, but we can simplify this. So functor is a type. For example, we know, because lists are mappable in JavaScript, we know that lists are functors. So map can be called on lists. So this means actually just give me a function from a to b, and I will give me a list of a, and I will give back you a list of b. I think that's fairly straightforward if you think about it. And why we tend to think about map like iteration is because maps implementation as in the functor of lists are iteration. So you go through the whole list and apply your function to every value. And that's not always true. So for example, let's talk about the type maybe. Maybe is maybe can have two values, just something. So it has two type constructors. It looks like basically this: data maybe a equals just a, or sorry, I don't find it, or nothing. This is how it's defined in this language. And so this is the type maybe, and this is a type parameter, a, which we don't really care about. And for example, if you have you run a search in a database, then you obviously don't really get back a result always. So this is a maybe type. This is what the maybe type is good for. You can represent your return as a maybe. And if we have a result, that's just the result. And if we have nothing, that's nothing. We don't really like throwing exceptions in functional programming because, as I have said, it's kind of a lie to throw an exception because you don't always return a value. You cannot return multiple values as well. You have to wrap your values inside a context if you have to return multiple values, like we did with the array. The functor box is basically giving you a context which you can map over, and you can map over maybe as well, but it does a different thing. So if we check back again, we have a functor in the list. It will be mapping a list of A to a list of B. In the case of maybe, it will be mapping just A to just B, or mapping nothing to nothing, because it's a different implementation. So basically, you are overloading the functor map function. And you can define your map function to the instances every time you want to create a functor instance. I will show an example of that as well. So for example, I can just show you a thing here. So a result array, if we write that out, it will be hello world because it be applied to upper. So this map has two parameters, a function and a functor. And we applied this to upper function to this array. So we get back hello world uppercase. But if we do this with a maybe, result just, we will get back just hello world. But if we try it with a nothing, you will get back nothing. So here is the nothing version. And you can nest these. So for example, we can map over the list of maybes with another map, and you can pass another function to that map. So this is how functors are different. And for example, we should just think about what other things can be functors. For example, we have something called a promise in JavaScript, which if you think about it with the signature of this map, you could say that then is really close to map, because if you are giving me a promise and a function from A to B, then and the promise of A, sorry, so a function of A to B and the promise of A, then I will give you back, well, if you do a new promise, obviously. So this is why promises are not functors, but then is really, really close to map. So it's really close. We have actually libraries which implement promise as a functor. But for example, you can always think about are functions functors. And this is an interesting thing. So if you think about it, and we check also again the implementation, if functor f, this f is a function, and you give back an A to B and the function of A, I will give you back a function of B. That means that you sneak under the second call. So you will get back f, or let me just, I don't know, let me just write it this way. So if you have a function of f, this is the functor, and you have a function which is the g from A to B, then you sneak under this function and you call this g over the f. So basically we are doing the same thing. Actually, we should look at the implementation of a real map somewhere. So I created a list, which this is quite easy in Purescript because list is some type of an empty list. So you can have an empty list or a head of a list and a tail of a list. This is how you create a linked list in Purescript. This is really nice. This is the most famous example in Haskell as well. It's not nice this way because you can create an infix operator for this build, but we will show that later. So let me just move on. So we can show this list, and I have created this example list. We build 1, 2, and 3, and then an empty list. So this will run like this. So we put 3 in the empty list. We put 2 in the list which has 3, and we put 1 in there. I know this looks ugly, but I will show you a different approach to this. Here is why I implement functor on my list. So you have an instance of functor, and you have to define map here. And what this map does is takes a function, and you can pattern match here. So Purescript has also the capability of pattern matching, which means that you can just do your kind of similar thing to regex, and or destructuring even. It's also similar to destructuring in JavaScript. So you destructure the head of the list in this X and the tail of the list in this XS, and you do some kind of recursion. So this is the implementation of map in a list. You take the head and apply a function to it, and then this dollar means that you execute this part later. So, and then you call map again with the function you gave and the tail of the list. And I can show you that this works actually by just showing example my list. That's a weird name. So we have 1, 2, 3. If I actually write empty here, then we see that it will print the empty list on the end. Sorry, I have to reload. Oh, never mind. Okay. Oh, I have some kind of code, some row code here, right? Here. Yeah. Okay. What is happening? Okay, figured it out. Great. So yeah. So we have this list, it doesn't really matter, and we can map over this list because we defined it. And I can pass in, for example, a function of partially applied multiplication with example, which will multiply my list. So you can do this with every kind of data structure. And I'm kind of fascinated by this because this is, you see, this is good because it gives a really general approach to how you can structure your types and data, and it is really maintainable, I think. So also it gives a great deal of safety. And if you get used to this kind of white space application, then it's really nice. Also recursion, I guess, and stuff like those.
Daniel,
Yeah.
is this on line 120? Is this an alternate version of what a map definition could be, or is this the canonical definition of what a map is?
What do you mean here, this map?
Yes.
Okay, so this is the definition of map in a case of my list, but in the case of maybe it would be different, obviously, because you don't have a list of values, you have a just value and nothing. So in case of nothing, you do nothing, and if there is a just value, you sneak under the just and just apply the function to the value. So it's similar, but it's different also. So this, what you have to understand is that this is specifically for the my list. It's like an interface of a functor, but my list implements it. That's basically what it is. Yeah. And you
So
are
this is the iterator for the my list, specifically for my
Yes.
list, because you
Yes.
might have three
But-
different types of data in it.
Yes, but Purescript knows which map you want to use, because if it has a functor instance, then it will get you the good map. Actually, it will infer which map you want to use. So it's like overloading map, basically. Yes. And this is pattern matching what you see here. So if map and we don't care about this function here, but we have an empty, then we will return an empty anyways. And if map has something and the build in it, then we will do this. So this is pattern matching. It's like a switch case, but you don't have to write out the switch case. Does that answer the question? I'm not sure.
Yes. Well, I guess the bigger question is, does the language itself have a generic version of map, or must you define the type of map every time?
The functor. So functor just says that you have to implement map somehow if you want an instance of functor and you want to map over your data structure. And you can tell how that map what will it do, but the structure is here. So this is the interface of map. This is true every time. You will have to return, you have to preserve the structure, basically. So that's what map does. It takes a functor of something and returns the same structure, but applying functions inside it. So in a context, basically this is what it is. I'm not sure if that's okay.
That makes sense.
All right.
So I guess
yeah.
the distinction here in general is that in a procedural language, you can you have the idea of iteration from 1 through n or 0 through n. And in this case, in functional programming language, there's no concept of iteration because there's no inherent order. So you must split the list by head and tail.
Yes, actually you are doing recursion here. So we are not doing loops in functional programming. We are doing recursion, and they say that explicit recursion is not good all the time, but sometimes you can write it out. Other times you try to use folds and traverse and and you have so functional programming provides you several tools to use your data structures, and these are predefined, so you don't have to actually create these lists. This is just an example of how you would do it if you want to. And this is the last thing I want to show. I guess the time has pretty much done, so we will move to questions. I said that this is a little bit clunky, this build. Where is it? Sorry. So the example my list, this is a little bit clunky, but actually for build there is an alias which is an infix function. It's called double dot. If you check the type of this, sorry, I'm not sure. So let me just try it. So you can do it like this actually, and it will build you a list. So this is the same, it's just the build is has an alias to this double dot in the real array implementation, and you can actually do this to build a list. So yeah, that's it. I'm not sure if I told everything I want to. Maybe the last thing I want to talk about is why it is good for us. And again, I can just repeat myself that most of the things functional programming has a solution to, and if we can learn to speak the same language, which obviously involves a lot of jargon and like monads and applicative and stuff like those. But if we can learn to speak the same language, then we will have a better understanding of code. We can reason about code better, I think, and it gives a great trust in our code. So it's about maintainability and the trust. And you won't really have runtime exceptions with functional programming if you are using like Haskell or Purescript, because the compiler is really strong, so it will catch everything basically. And that's it. So if you want me to explain why monads are just monoids on the category of end of functors, I can do that as well, but I don't think that's necessary for now.
I have a more general question, if that's all right.
Sure.
So on a lot of our projects, we're using TypeScript.
Yeah.
And that is being used in production for lots and lots of things.
Yeah.
Do you think that something like Purescript is mature enough to use in production for the types of projects that we work on?
I think it would take a lot of learning, but yes, Purescript is mature enough because several companies are using Purescript in production actually. So you can build UIs with it because it has a React implementation, and it has also several server implementations as well. So you can do basically everything with it because it just compiles to JavaScript, and you can, oh sorry, I forgot to mention that you can also import functions into Purescript from JavaScript and annotate them. So that's also possible. There is a thing called the foreign function interface. So yes, definitely yes. I would give my hand, one of my hands maybe, to do something in production with Purescript.
And given that and all of the tooling that you might need to support that, do you think that Purescript would be the best option for writing, with a functional language for the browser, or are there other tools out there that you think are worth consideration as well?
Well, there are several things. If you want to learn real functional programming, it's either Haskell or this, or like there are other options which are similar. You have more popular options, like for example Elm, but I don't really like that because it's like a simplified version of functional programming. You don't really have type classes and the amount of polymorphism Purescript is capable of. So there are a lot of tools out there, but Haskell and Purescript is the best, I think, to learn functional programming. And why I chose Purescript over Haskell is because Haskell's environmental things are really messy. So it's hard to set up, hard to try out, hard to do something real in it. And in the other hand, Purescript is different because you just run an npm install and you have the compiler and you can do stuff. So it's easier. All right. Does that answer the question?
Yeah, that's great. Thank you.
Okay.
So I had a follow up on that. Wasn't there the author of React? Didn't he come up with a Reason? I might have changed its name. Have you used that? Because that
I have seen Reason ML. Yeah, Reason, not Reason. It's not. It's Reason ML, right?
Yeah, I think it might change its name. Or yeah,
I have seen
is
it.
that not? Does that follow some of the same patterns here? And does that fit well into the sort of React ecosystem?
I think Reason is more close to JavaScript than TypeScript. You have like strong typing there as well, but it's more similar to TypeScript. I'm not an expert on the topic, so I don't know exactly. I have seen it, but I like
it's OCaml, so I think it's all the same backgrounds, but yeah, it's another thing worth exploring.
Yeah, I think probably yes. It's just these are more, Purescript is more like on the academic side of the things, and that, I mean, it's a matter of preference, but I like that. I like that this has all the structures that a real functional programming language has. For example, you have to denote that you are performing an effect in a function, and if you install a library, you can be sure that it won't mine Bitcoin, because if you are mining Bitcoin, you have to make that signature in your function, so it's not doing anything hidden. I'm not sure if Reason is similar in that manner. Didn't read too much about it.
Sure, thanks.
Okay. Any questions? More questions? Nobody. I think then we are kind of finished the talk, and I'm right on time. That's great.